Okay, well, welcome everybody to a seminar series in geography and spatial sciences. Celine, you'll be happy to know that you're being recorded. Alexey knows about your channel, so I'd let him know about that. So anyhow, it's my pleasure to introduce Alexey Shiklomanov for our talk today. Alexey was an undergraduate here. He graduated, I had to ask him, I forget the exact year, it was 2014. He's a double major from the University of Delaware's chemistry, like Celine, you know, chemistry, and environmental science, being a double major. And then he went on for graduate school at Boston University and received a PhD from BU. And for the last 5 years, you've been at NASA Goddard, right?
Yep. Yeah.
Okay.
Keep the postdoc in there. That's okay.
He had a postdoc before going to NASA Goddard, but Alexey's a really great person. A lot of you met with him today, a number of faculty, some will meet with him after, and he's gonna go with a few graduate students, the Little Goat, and introduce him to some good coffee if he's a coffee drinker. So with that, I'll turn it over to Alexey and we'll go from there. Thank you.
All right. And this ends at 2?
Yes, we have till 2.
Okay, yeah, so I have 130 slides. We'll just get through this. Only 29. Great. Well, thanks so much for coming around for the afternoon. Yeah, so Del, thanks for the intro. Thanks for hosting me. So I'm Alexey Shiklomanov, research scientist at Goddard. And I wasn't sure what to come to talk to you all about. But it sounds like you know, with Del's leadership and other people, there's been a big push towards more data science and more big data, sort of GIS analytics. And so being at NASA, I can't give you a presentation that doesn't focus on cool NASA satellite stuff. And so the goal of this presentation will be to mix some of that with some of the informatics challenges that we're facing in terms of NASA operations. So I'm going to give a brief introduction to some of the cool stuff that we do at NASA, and then I'll sort of in the second half of the talk focus more on how we actually do it in terms of data management, data processing, and things like that. So first, briefly about me. Born in St. Petersburg, Russia, grew up in Wilmington, Delaware, went to Mount Pleasant High School, go Green Knights, 2010 to 2014, go Blue Hens, BS Chemistry Environmental Science, and Del was actually my undergraduate thesis advisor when I did work on STEMflow. And at the time, my research looked like this. So this was all material that you can buy for relatively small amounts of money at Home Depot. And then we went out, we collected rainfall after each rainfall event, and this was a bunch of work, you know, going out there after every rain event over a given summer, and then I think also into the fall. So it was like 6 months of work. And at the end of all of this, I collected like 15 data points. And I was like, man, there's got to be a better way to do this. And so that's sort of what brought me to my grad school at Boston University, where I looked a lot more at trying to squeeze as much value as you can out of as many observations as possible. So both using a lot more data sets from satellites, from airplanes, from big ecological research networks like NEON pictured here, from big plant trait databases, but also, you know, trying to do that in some way that makes sense, right? Not discarding the value of those observations, knowing the amount of blood, sweat, and tears that goes into every data point. So I did that, PhD in geography at BU. I did a brief postdoc at the Joint Global Change Research Institute. That's part of the Pacific Northwest National Lab. And then since 2020, I've been a research scientist at NASA Goddard. So briefly, sort of what is NASA? What is NASA Goddard? I'm sure everybody knows NASA. NASA comprises a bunch of different centers pictured here. Goddard sits here in Greenbelt, just outside of Washington, D.C. We are NASA's largest center, and we are the largest combined organization of scientists and engineers in the U.S. So there's about 10,000 people there, scientists, engineers from every earth science discipline, also heliophysics, planetary sciences, and so on. So NASA founded in 1958, Goddard was commissioned in 1959. So like after NASA became a thing, the first building that they built was the NASA Goddard Space Flight Center. And so some of our flagship things include the Hubble Space Telescope, Nancy Grace Roman is something we're working on, the Terra and Aqua satellites, which host the MODIS instrument, if you guys are familiar with that. And then we also operate satellites, some of ours, but also some from other agencies. So Landsat for USGS and the geostationary data from NOAA. So the current NASA Earth fleet looks like this. You can see it goes back to roughly 2000 with the Terra and Aqua satellites. This is the Earth observing system era. And then it spirals out into the present. Here we are in 2025. NISAR has been 3 months from launch for the last year, but maybe one day we will actually launch it. That's in partnership with the Indian Space Agency. But some of our recent cool launches include PACE, which is a big global oceanography mission. SWAT is a big one for surface water topography, if you're interested in how much water there is in rivers and oceans. And of course, some other things here that are hopefully familiar to you, like Landsat 9, for example, as a continuation of the longstanding Landsat program. And so I love to talk about how cool all of these things are. So my first couple of slides will just be some interesting science, or really even just basic applications that you can do with remote sensing imagery. So this is looking at Landsat. One of the most basic things we can do with optical passive remote sensing imagery is just to look at it. And so here you are seeing the evolution through time of the city of Shanghai. You can see in the bottom left there the years. And so without doing any complicated data science, all of this fancy machine learning stuff that you guys are learning here, just looking at this image, you can really see quite a lot of urbanization happening here, right? It doesn't take a ton of stuff to see just the extent of urbanization, the extent of deforestation that happened around Shanghai over the last 30, 40 years. But this is the kind of thing that we can do with a long continuous satellite record. And this remains something that is relatively unique, I think, at the US government, that we have these long multi-decadal satellite data records they can use to study these long stretches of change. Sometimes we like to leave our satellites on at night. And so this is a nice example from the VIIRS instrument, which is a collaboration between NASA and NOAA. This is the specific thing called the VIIRS Night Lights dataset. And so here we've just taken that same passive optical instrument and just left it on at night. And so what it's soaking up is not the reflected sunlight, but where you have lights on radiating from the Earth, basically where people have their lights on. And this is a really nice, striking illustration of how this is a really powerful indicator of socioeconomic activity, right? And so here we are looking at basically the concrete impacts of the Syrian civil war. You can see that here Aleppo exists as a bright yellow spot, and then after the Battle of Aleppo, there is now complete darkness, right? All the people have been displaced, the lights have been turned off, the energy infrastructure completely destroyed. You can also follow some of the interesting changes to see where refugee camps have settled, for example. And so VIIRS, the black marble data set shown here, is a really powerful tool for studying the impacts of disasters, disaster recovery, and things of that nature. So both of those things are in the passive optical domain, right? So those are things that we can see with our own eyes, red, green, blue, right? From 400 to roughly 900 nanometers. Pop quiz, does anyone know what city this is? All right, geography department. This is Tokyo. All right, this is a passive true color image, again from Landsat. You can see where the city is in just straight red, green, blue imagery. What we can also see with the same instrument, but staring out at further wavelengths, is what the city looks like in terms of its heat. So this is now a passive thermal remote sensing measurement of the same city. And one of the things that jumps out here, bright colors are hot, bright colors are cool, dark colors are hot. You can very clearly see jumping between these two images, right? Out here, a lot of natural vegetation, a lot of forests, right? Those provide a nice cooling effect through evapotranspiration and other things. Whereas where you have dense urban cities, where you have fully built up infrastructure, right, impervious surfaces, things that have a low albedo, they're very dark, you can see significantly higher surface temperatures, right? And then this massive blob in the top right corner is a high atmosphere cloud, right, which is transparent, or opaque, excuse me, to the infrared. So in this way, we can just study not just cities, where they are and how they're growing, but we can also study their actual physics of the cities, right? For example, this kind of thermal imagery is incredibly useful for studying the urban heat island effect, for example. If there is a heat wave, it is much nicer to be out here in the woods than it is to be out here in the much hotter center of Tokyo. So, of course, we can zoom out and do these things globally. So this is a nice animation, again, using a thermal measurement, this time from the VIIRS instrument. And each one of these little dots that you see animated here is an individual fire detection. So again, we're using passive thermal imagery, right? This is, and then when fires are lit, of course, they are very hot. And so we detect that as a spike in the thermal signature. And in fact, the amount of spike that we see in the thermal signature roughly corresponds to the intensity of the fire. And so one of the things that's interesting about this graphic is we think about the fires in California or in Canada as being really bad. But in fact, if you look globally, they are completely nothing compared to the amount of fire that happens in sub-Saharan Africa every single year, more or less all the time. right? And so we can see from a graphic like this that fires are a global phenomenon, that we can study them, we can track them, we can do all kinds of interesting science using these measurements of where fires are. So those were all passive measurements, which means that we just have effectively a camera with no flash, right, that's flying around in space. So it is just collecting signals that come in. Another class of remote sensing that we have at NASA is what is called active remote sensing. So this is where we are actually shooting things out from the satellite and measuring the return. And so the example I like to use here is of an instrument that's on the International Space Station called the Global Ecosystem Dynamics Investigation, or GEDI. And so this is what's called a waveform LiDAR, which means it shoots out photons. It then measures how long it takes the photons to come back. If you know the speed of light, that then can be translated into a measure of distance. If you know roughly where the surface of the Earth is, you can translate that into a measurement of height from the surface. And so what you are seeing here is a global map that we have generated of tree height across the entire world. And so this kind of thing is incredibly useful if you're trying to figure out how much biomass is there in the Amazon, for example, or how much biomass is there in the Congolese rainforest or other places. And how is that biomass changing? Where are we losing forests? Where are the forests changing in their structure? The reason that that the Earth in this graphic, you can't see it because the little bar there, looks like it's got a little bit of a cutoff there at the top, is because this is an instrument on the space station, which only has an orbit from 55 north to 55 south. So you don't actually get the polar regions using this instrument. And so what does this instrument actually look like? It looks something like this, right? So every single one of those little things that you saw on that previous graphic is actually a return from one of these beams that are coming around in parallel. And you can see what's cool about waveform LiDAR is that you're not just getting the tops of the canopies here. You're not just getting the overall canopy height. You're actually getting a full three-dimensional profile of where the plant stuff is, right? So this basically gives you not just canopy heights, which are these lines that you see here along each of these beams, but you're actually also seeing where's the vegetation densest. Is it densest near the surface of the forest? Is it densest, closer to the tops of the trees, or something in the middle? And so this is an invaluable tool if you really want to understand how forests work and how they're changing. So GEDI is a really cool instrument. So we've talked a little bit about active measurements. We've talked a little bit about passive measurements. Now I want to talk about one of our weirdest instruments, which is actually really cool. This is an instrument called GRACE, which stands for Gravity Recovery something, Climate something, whatever. The measurement here is you have two satellites flying, pointing at each other, and what you're measuring very, very precisely is the distance between them. So this beam here is a constant measurement of distance, I think down to the micrometer or even nanometer scale. And so what happens here is when you fly over a region of slightly higher gravity, of a place on the Earth where there is more stuff, you get an elevation of the amount of gravity. And so then one instrument will sort of accelerate ahead of the other one, and the other one will catch up. And so this kind of stretching and compressing action is a way of measuring the Earth's gravity. So why would you want to measure the Earth's gravity? Because A, you want to understand sort of like what is the geometry of the world, but B, gravity is actually a really nice way of understanding how things like ice sheets and groundwater are changing, right? And so, for example, when you see large-scale declines in groundwater, these show up as a reduction in the Earth's gravity over those regions. When you see large-scale declines in sea ice, for example, you also see declines in the Earth's gravity. And so we can think of, gravity as being this constant that we all experience on Earth, but really, as a figure like this shows, we have huge spatial and temporal variations in the Earth's gravity that correspond to changes in things like groundwater, sometimes to seismic events, to ocean currents, and other things. So how do we use this? Here's a nice example. So what you're looking at here is how wet is the surface of the Earth, and then how much water is there at further depth, so at the groundwater level. And so one of the things that we can see from a graphic like this is we can see that the root zone soil moisture, which is basically that top layer of soil that plants are actually using with water, this is something that's highly relevant to agriculture. This is highly relevant to how plants are actually working any given day. You can see that that varies a ton day to day. Some days it's hotter, some days it's colder, right? Some days it's wetter, some days it's drier. But then the underlying groundwater changes much more slowly, right? That changes in response to longer term changes. And one of the things that we do with NASA is we combine a bunch of different observations, like the thermal that I showed you earlier, but also the groundwater measurements that we get from something like GRACE. to produce real maps of things like this, right? Where we're understanding the hydrologic cycle at multiple vertical levels of the Earth's surface. So that's a hydrology example. Here's a cryosphere example. The figure on the right here, this is of course Greenland, is the total amount of ice sheet mass of the Greenland ice sheet. And then what you're seeing here are actually lines showing the flow of that ice through time. So how is the ice flowing off and melting? And so the big red blotches here are places where Greenland is melting more rapidly. And then these measurements here with the various dots are showing you how the elevation is changing based on, again, a LiDAR measurement, this time from a measurement called ICESat. And so again, a nice example of combining two different types of measurements that we have at NASA, of GRACE, which gives you gravity, of ICESat-2, which gives you altimetry, basically height, to measure something about the Earth system. So what does a satellite orbit actually look something like this. So this is an illustration of Landsat 8, just a single satellite. And why this is important, I'll get to in a second. But this is sort of setting the stage for what do satellite observations actually look like. We do not ever observe the entire Earth all at once, right? What we observe is a strip of the Earth at a particular time, at a particular place. And so when we stitch together these quote unquote global maps, we're not really seeing the world globally. We're just stitching together observations created at different times. And then the more instruments that we have at any given time, of course, the better of a picture we can craft of the Earth as it goes. So this is going to be important in a second. And so here, the instruments that we're showing are the combination of Landsat 9 and Sentinel-2, which is a European instrument. And based on these, we create what's called a harmonized Landsat Sentinel dataset. So if you're ever looking at good long time series with a lot of observations, HLS is a great dataset for doing that. So what does this data actually look like? If we step back and do an even more complicated example, one of the things we do at NASA is we actually do some weather forecasting and climate reanalysis. So that means that we take a bunch of observations from all kinds of different things and we stitch them together, combined with our physical understanding of how the atmosphere works and how the ocean works. And we use that to craft a continuous product. So again, to illustrate the point of like the data management challenges that you face in Earth observations, right? If you look up here, surface conventional, these are basically balloons, floats, things, or not balloons, sorry, ground stations, floats in the oceans, things like that. This figure up here is showing sensors that are literally on commercial aircraft, collecting temperature and pressure measurements wherever they are. Upper air conventional measurements there. A bunch of satellites from a bunch of different places. So here are some NOAA satellites following that traditional polar orbiting pattern. Down there, you can see some geostationary satellites, the ones that look like globes that are looking at the entire world. Point is that when we try to create a continuous data product, we're often dealing with satellite observations that look like this, right? They're either point measurements at a particular location, or they're discontinuous observations from a bunch of different instruments at any given point in time. And so when we go to craft a proper data product, our final data system looks something like this. And so that's over the course of 7 days, all of the observations that we use in one of our Earth system models at NASA. So just one more illustration of what raw satellite data looks like. These are measurements of what's called aerosol optical depth from a measurement on the AURA, the OMI instrument. And so you can see broadly some kind of patterns emerge here. You can see that there's greater thickness of the atmosphere, which means you can't see as well. There's more stuff in the atmosphere, more dust. Here, Australia, here coming off of Africa, here in the Asian subcontinent. But there's a bunch of noise in this data set. There's a bunch of gaps. The gaps are from clouds. The gaps are from the fact that our orbits are crossing each other. And there are some regions of the equator that our orbits never touch at all. And so when we get satellite observations, they often look something like this. And so where I work at the Global Modeling and Simulation Office, we take observations that look like this, combine them with a bunch of other stuff, and then ultimately generate data products that look something like this. So here, no gaps everywhere in the world. This is land surface temperature, right? And so what this is giving you is any given hour of the day, what is the 2-meter air temperature at the surface of the Earth? This is through a process that's called data assimilation. Those of you that have worked in meteorology probably are familiar with this, right? This is the process of running physically based models and then adjusting them to match observations. And so we do this with a huge variety of different observations that are coming in, some passive, some active, some thermal, some optical, some radar. And so this is a very simple example of temperature. We do this also for precipitation as well. This is a product called iMerge, the integrated, I don't remember our acronyms, but it's an integrated measurement of where we have precipitation going on anywhere in the world at any given time hourly. And this product is produced within 30 minutes of near real time in its lowest resolution. So this gives you both the volume and the character of precipitation, combining a bunch of different meteorological satellites. So these are the kinds of problems that we routinely work on at NASA. And finally, one of my favorite examples of this is this animation, which is showing you not just one species of aerosol, but actually 5 different aerosols from a simulation. You're looking at carbon, sulfate, dust, sea salt, and nitrate. And the interesting chemical and physical interactions between all of these things over the course of a single summer. And one of the things that you can see here is these big red plumes coming off South America, coming off of Africa. These are the big fires, and you'll see the big Australia fires that happened a few years ago start to emerge from the east coast of Australia here shortly. But you can also notice just all of the complicated chemistry and physics that's going on here, right? You can see the storm tracks of individual storms reflected in the sea salt that is being kicked up into the atmosphere by those storms. You can see anthropogenic emissions from big industrial centers. These are your nitrates, right? Over here in China, over here in the United States, over there in Europe. And so, again, one of the big things that we do at NASA is we make a lot of measurements of all kinds of different kinds of measurements from satellites. We combine them with all kinds of other information as well. And we finally produce these kind of cohesive data products that look something like this. And by the way, if you have a keen eye, you'll notice there's some kind of stuttering in this animation. That is an actual visualization of that data assimilation step, right? That actually is showing you where we are adjusting the predictions of all of these things based on when satellite data are actually available. So that's getting nudged every single one of those orbital overpasses to better fit the truth. Okay, so coming back to our Earth fleet, what is the combined catalog of NASA Earth observation data? It is something like 11,000 data sets, which we call collections from about 1,100 different instruments, totaling approximately 150 petabytes of data spread across 1.7 billion files. All right, so that's a lot of data. Anecdotally, I've been trying to sort of figure out how to think about this number, 150 petabytes. My understanding is that it's about the size of a single copy of the entire Netflix catalog. So if you were to download every movie and TV show on Netflix, I think it would total roughly 150 petabytes. Of course, Netflix duplicates all of them, so Netflix's actual data storage is something like 10 exabytes, based on the most recent estimates I could find. But a single copy of the catalog about the same size as ours. So how do we actually manage this? I've shown you a bunch of cool animations. Now I'm gonna hit you with an org chart. All right, so this is gonna be fun. So at NASA, we have headquarters that sits up here. We have a program called the Earth Science Data Systems Program. One of the elements of that program, the biggest element, roughly 90% of the funding, is this thing called the Earth Science Data Information System Project. And within that, you have a couple of sub-elements. You have a bunch of people that actually do the processing of the individual instruments. So I've highlighted some of them here. For example, these are all instruments from the Terra, Aqua, and Aura satellites. And so you can see, for example, OMI is one of the ozone monitoring instruments on the Aura satellite. You can see some other things like MOPID is a tropospheric chemistry measurement. So we have scientists in charge of processing these things, working in close collaboration with engineers. But this is geographically distributed. Then separately from that, we have basically these individual data libraries. So these are what are called decks. And so here you can see that some of them are sitting at actual Goddard centers, or at Goddard or at the NASA centers. So at Goddard, we have 4 of these data centers: the JESDISC, the OB deck, the Crustal Dynamics Information Center. But then some of these sit at other NASA centers, and some of them don't actually sit at NASA centers at all. So actually, NASA relies a lot on its partners to both host and process these data sets. So for example, the Alaska Satellite Facility sits at the University of Alaska Fairbanks. The Oak Ridge National Lab DAC sits at the Oak Ridge National Lab, which is the DOE National Lab. Snow and Ice Data Center sits at the University of Colorado Boulder. So we have these geographically distributed data libraries, and then we also have some combined capabilities that access this entire data catalog. And so one of the things I'm going to show you now is just a quick overview of some of the ways that you can actually access and work with all of these various NASA observations. And then I'll finally end with some of the challenges that we're facing moving into the future. So one way that we organize these data sets is through a central catalog of files. This is a thing called Earth Data Search. This is a unified search and discovery interface for all of those 11,000 collections. All of those 1.7 billion files can be found through a search interface that looks like this. This is completely freely and publicly available. I encourage all of you to use it. If you aren't using it already, shame on you, because it's awesome. So it's a cool interface. It lets you filter by time. It lets you filter by instrument. It lets you filter by space and certainly do arbitrary keyword searches. This should be your initial entry point into any kind of NASA Earth science data. Zooming in, for those of you that like programmatic access, the Earth Data Search is actually a front end around this complex API, which stands on top of an Elasticsearch database, for those of you that are interested in such things. This is an API that you can use to basically accomplish the same exact thing. This is called the Common Metadata Repository. This is the system that we use to organize all 1.7 billion of those different files. And more recently, we have created a convenient Python library that makes it easier to access this stuff as well. So this is the Earth Access Python library. This is a multi-DAC collaboration, a really, really cool effort that really streamlines a lot of this process. And don't worry about taking photos of this. I'll share all these slides at the end so you can have all these links and various things like that. You know, one of the things that we've done over the years is gradually improved and sought to continue improving our access. The way that we distribute these data sets to make it more and more easily accessible, so that people can do more science and more cool applications. So that's sort of straight up data access. One of my favorite capabilities at NASA is also this. This is a visualization capability that covers a subset of our catalog, but is incredibly powerful. This is a tool called NASA Worldview. And so here we are storing, for over 1,000 of those 11,000 collections, we are storing pre-generated imagery of these things that is easily browsable. You can do animations. This is also a great tool for data discovery. There's actually tight integration between NASA Worldview and our core catalog. And then there's also some interesting widgets here as well, like this comparison tool for comparing before and after. In fact, one of the animations I showed earlier was generated using Worldview. And again, this is a great way to sort of interactively find data sets that you need. And then there's that data download button that lets you access these things. Worldview is really just a front end around a WMTS endpoint. For those of you that are studying GIS API standards, that's a very common one for mapping. This is a thing called the Global Imagery Broad Service, or GIBS. And so you can actually, in a Python notebook, in an RStudio environment, you can use sort of web-based queries to generate these same data sets, to visualize them directly in your analyses. And so this is a great way, particularly to get background imagery, if you're drawing a map of any kind. So this is incredibly powerful. And again, fully open. And then, so those are all kind of things that are true across all of our libraries. But historically, each of those individual data libraries or DACs have also developed their own tools for their own subsets of that NASA catalog. So for example, this is a great tool called Giovanni from the Jez disk, and that's cut off there, there at the top. It's an analysis and subsetting service. Here's one specific for soil moisture visualization from the Oak Ridge National Lab DAC. And finally, here's a nice example of a data access and subsetting service from the LP DAC, which is operated by USGS. So these are all really powerful. The way that these DACs are ultimately organized is focused on specific subdisciplines. So for example, if you're an atmospheric scientist, you will often go to the Jez disk first because most of our atmospheric data sets live there. If you're a terrestrial ecologist, you might go to the Oak Ridge National Lab DAC because that's focused on terrestrial ecology. If you're interested in sort of like large land surface remote sensing data sets, that's usually where you would go to LP DAC. But of course, one of the things that's an issue is that some of these data sets are useful for a bunch of different disciplines. And so we'll get to that in a second. So that all worked pretty well for a while, but now we've got some unique challenges, especially over the last couple of years. And so we'll talk a little bit about some of those. So one is that traditionally, and maybe you even saw this from the way that I talked about our approach to data distribution, data processing, is if you go to NASA, probably one of the frustrating things you find, you're like, what's the temperature? I just want a land surface temperature product, right? And what you'll get is, well, here's what eco-stress land surface temperature is. Here's a Landsat land surface temperature product. Here's a MODIS land surface temperature product. Here's a VIIRS land surface temperature product. They're all at different resolutions. They're all over the place. And so you're saying, just give me the damn temperature, right? Like one of these things in any combination. And so this push for transdisciplinary multi-mission science is a relatively new thing that we're actually trying to do at NASA, or at least it's a strategic vision from headquarters. That's kind of pushes against this idea of data libraries that are each responsible for a subset of our catalog. Another one is dramatic increases in data volume and complexity. So in fiscal year 21, this is a few years ago, we were sitting at 62 petabytes. Just in the last 3 years, we have tripled that number already, right? So here we are now in FY25 at around 150 petabytes. The main reason that we aren't even higher at 200 petabytes is because NISAR hasn't actually launched yet. If it had, that alone brings in an additional multiple petabytes of data. So big data volumes and projected to grow even larger, right? Here we are at 150 in 2025. 5 years from now, we're going to be pushing 600 petabytes, right? So 4 times the size of the catalog, even from the present day. And finally, an increased emphasis on open, accessible, and reproducible science. This is something that we've seen across all the science agencies, at least. And so NASA has been at the forefront of trying to do more open science. And that means allowing people that do not have big HPC clusters or a lot of technical expertise to be able to work with these data sets, right? Because those are the places where they'll be the most valuable. And so that brings me to the more technical part of this presentation, where we'll focus a little bit on the commercial cloud computing, and how that plays into all of this. So why the commercial cloud? So the traditional way that we've done these things is through institutional high-performance compute resources. These are powerful, they're very cost-effective if you're running them at full capacity, but they're also highly specialized. They're not well-suited for everyday analysis tasks. They require effort and expertise to maintain, and they're usually closed off to the public, right? I never did enough computing at University of Delaware to use any of University of Delaware's HPCs, but if it's like any of the other HPCs I've worked on, it's a massive pain, right? You have to sit around in a queue. Probably you have to use an outdated Linux operating system, right? You do not have admin privileges to install what you need. And so I like to talk about these things in terms of transportation metaphors. And so when I think about institutional HPCs, I think about a fleet of trucks that your institution owns, right? These are very, very good for a very specific thing, which is moving large boxes around from place to place. I would not drive one of these to a grocery store if I could avoid it, right? But in practice, when we try to do sort of like lightweight science using these clusters, it's kind of like using a massive truck like this to go do some grocery shopping. And so the commercial cloud is kind of like a rental car service, right? It gives you a bunch of well-maintained hardware options, and it gives you a pay-for-what-you-use model. And so at any given day, if you feel like shelling out $100 to drive a Ferrari, you can. If you want to rent and try out a hovering car to see if that works, maybe you'll be able to do that too. You want to try an electric car, or maybe even want to try a big institutional HPC type system. All of those are options that are available to you, and you can customize the compute for the task that you need. So in the context of NASA, what does this look like? So in the traditional days, and this is still the model that we roughly experience, it looks something like this, right? You are, in this example, an ecologist, hence the fancy leaf graphic, and you want data product A, E, F, and H in a box, because that's how you like your data products. You like them all in a box. And so you go to your ORNL deck, that's your ecology entry point, but they only got 3 data sets. And they're only going to give you the data sets in the box, but they're only going to give you A, because that's all they have, right? Then you're going to say, okay, well, where else are the data sets that I need? Well, some of them are sitting at the Snow and Ice data center, but they don't package them in boxes, they package them in document crates, right? And so you're going to get those data sets in a way that you don't want. You want them in a box, but you're getting them in separate document crates. And finally, you have to get your final data set H, You have to go to yet another data center. So now you're at 3 data centers just for 4 data sets. And it turns out that they prefer to deliver things to you in shopping bags. All right. This is probably a metaphor for how a lot of you have done sort of like multi-data processing, right? This is often how it looks, right? You go to like 5 different locations, you get the data in like 6 different formats. You got to deal with like 3 different APIs at least, right? And that's all before you can actually do any science. And so the vision of the cloud is something like this. Same problem. You start out as an ecologist. They want A, E, F, and H in a box. Except now, instead of these things hanging out on a physical disk at any of these individual archive centers, they're all stored in a single commercial cloud data lake, if we're being fancy, basically a giant database. And now Oak Ridge doesn't actually own those data sets. It just says, you know what? I'm going to deliver them to you, and it can deliver them all to you in a box because it has access to all of them, right? It's a single shared pool of data. If you're a Snow person and you like things delivered to you in document crates, you might go to the Snow Nice data center and deliver those same data sets to you in those document crates. And it might turn out that internally, it makes a lot more sense for them to use 4 rental cars to deliver that to you than a single dump truck, right? It gives them the flexibility to design data services using whatever compute makes sense, not just the compute that they currently have, right, for any given data service. And finally, same kind of analogy here. If you're an atmosphere person and you want things in shopping bags, then you go to your atmospheric data center. They deliver all the data sets that you need in shopping bags altogether. And an option that did not exist before but does exist now is this last one, right? So maybe you don't want these things delivered to you. Maybe you want to grab your own car and drive it to the warehouse and plug in and then do work exactly on the data where they are. And this is an option that is now enabled because we're working in the cloud, because these data set, you're not trying to like access secure government compute facilities, right? You're just accessing the public commercial cloud. So to summarize, where we are right now for distributing all these things is a world, or where we were, I guess, is a world that looks something like this. You had separate data stores for different data libraries, and then you'd have to go to multiple places, interact with multiple services. Where are we now? We're moving into a world that looks like this, where we've decoupled where the data are stored from how they are analyzed, right? And this gives us a lot more power to do multidisciplinary science and things like that. And we've also added this additional analysis in place capability. So this is the future of NASA data. In fact, I think almost all of our big 150 petabyte data catalog has now moved into Amazon Web Services. And this is one of the reasons why, is that now we can enable these big multidisciplinary data analyses. So that's all great. But there's some problems with the cloud. And this is one of the things I spend a lot of my time thinking about. So one of the challenges is that working in the cloud is just different, right? If you're used to working on local hardware, there are things that don't work as well in cloud-based processing. And I'll get into some technical examples of this in a minute. One of the huge ones is this one. Cloud costs are, they're really high to begin with. So commercial cloud is expensive. If you've ever worked on AWS, you discover often, unfortunately, how expensive it can be. And more importantly, because it's sort of a pay for what you use model, those costs can be unpredictable and individual mistakes can be quite expensive. I've had postdocs in my lab try to do some analyses, misconfigure one thing, and then in a couple hours, they can rack up $3,000, $4,000, $5,000 of cloud computing costs by accident. Very easy to make that kind of thing. This is an interesting one. If you own a computer, you can, whether or not you use it all the time or just a little bit of the time, it costs you the same, right? You've already bought the computer. And so now if you use it 100% of the time or 10% of the time, you've already paid the cost for it. In the cloud, there's a direct connection between performance or engineering decisions and cost. If you use the cloud twice as much, it costs you twice as much. If you're storing half the amount of data, it costs you half as much. And that's sort of a time integral as well to that. Whether or not we like it, we're still stuck, or we have the opportunity to use, depending on how you want to frame it, a bunch of these institutional high-performance computing centers that we've built up all over all of our universities and research institutions. And combining these 2 resources is tricky. And so finally, this isn't really a cloud computing challenge, this is just a general challenge. Hopefully from the first half of this presentation, you saw just the sheer diversity of both the kinds of data sets that exist out there, even within just NASA, but also the kinds of analyses that you can do with those data sets, right? If you're doing snow analysis, you're probably doing different things than if you're doing terrestrial ecology analysis or hydrology analysis or oceanography, right? All these disciplines have different use cases. They have different data sets that work better or worse. And there's no technical solution to that problem. That is just, it is hard to do multidisciplinary stuff. So just to dive into a couple of these examples, it's hard to do apples and orange comparisons, apple to orange comparisons here, apples to apples comparisons, excuse me. But just to give you a sense, right? If you store a petabyte of data in the cloud with no particular negotiated rates, it'll set you back around $250,000 a year, right? And that's per year. So if you're storing that petabyte for 2 years, that's $500,000 and so on and so forth. It's hard to, again, get sort of ballpark estimates on this, but like if you were to just buy a bunch of disks, this is an estimate I got from a colleague that did this recently, right? You're talking about $70,000 and there's no per year, right? You just bought them. Quite expensive. Compute is even harder to compare, sort of apples to apples, but ballpark, again, if you're running roughly that kind of thing, it'll cost you about $20,000 a year. You can buy the same computer and run them for about $17,000 and it'll run as long as it goes until it dies, right? But there's more we need to consider, right? Can you actually do the thing you're trying to do using institutional HPC, right? Even like basic things like looking at pictures on an HPC that you're SSHing into, right? It's hard to do, you can't do it, right? If you want to run a website, if you want to run a database, if you want to run any kind of background daemon, all these things are really tough to do on HPC systems, right? You would never build a lab website on an institutional HPC, right? That would be crazy. This is another interesting one. What is the minimum amount of compute you need to buy at a time? Oftentimes, we don't actually want to do like a year's worth of processing, right? Running every day, all the time. What I sometimes want is it's like the week before AGU, and I'm really sitting in that cluster, right? Waiting for my job to start. And I'm like, I will literally pay $10 out of my own pocket to get an instance to run my job for 5 hours, right? In the cloud, you can do that. So that minimum amount of compute that you can buy at a time works as well. How quickly do you need to scale compute up or down? The interesting thing with the cloud is that if you run 1,000 processing jobs in parallel, or you run one job for 1,000 times, it costs you the same, but doing it in parallel takes you 1,000 times as fast, right? You can scale out horizontally as you need, then bring down the compute that you need. A lot of, not all, but a lot of software, a lot of scientific programming tasks fall into that category. This hardware thing is interesting. I was at a meeting recently, a summit on artificial intelligence that was organized by Microsoft for the federal government. And one of the things that struck me is that one of their headline presentations was from the Department of Energy and how they're using cloud computing. And I was like, wait a minute. Department of Energy has like the best computers in the world, period, full stop. If you look at the list of top 10 HPCs in the world, like 7 of them are national labs. And so I was like, what are they doing shelling out obscene amounts of money on cloud computing when they've got these awesome data centers? And what it turned out is that Azure, Microsoft's cloud computing, could get their hands on the fastest, the newest generation of GPU chips that you need for artificial intelligence, way faster than the Department of Energy could with all its hamstrung procurement mechanisms. And so what they needed to do was do this big, massive AI ML training thing that required a bunch of graphical processing units that happened to be available on the cloud, and they could get to them immediately, right? These companies are often the first to get their hands on this hardware, and that's really where some of the innovation in software engineering really is. And finally, this is what I like to remind people when they complain about cloud being expensive, right? If you're sitting there like debugging environment issues on an HPC on your legacy Linux system, right? That is labor hours that are costing money, right? Now, a lot of you are like grad students or postdocs, so you're pretty cheap, right? But like if you're a faculty member or or a contractor or something like that, this can really add up, right? And especially when you start to look at like, 2 cents per gigabyte month, on that scale, it's really not that much. So it's often cheaper if we save your labor hours and shell that out instead on cloud computing costs, or it can be. All right, now I want to talk about a very, very specific technical problem, and I've spent a lot of time thinking about this one in particular. This is an example of how things that work on normal computers, quote unquote, don't always work well on cloud. And the specific example here is like reading a file. So the amount of time it takes to read a file, to a first approximation, is like how long it takes you to even get to the file, plus the volume times the bandwidth, right? And so on the disk, you have relatively low latency. You can get to that file pretty much immediately, 1 to 10 milliseconds, maybe even less for a solid state disk. And so a lot of the times our files are organized around this idea that you can just get to them, right? And you can read them, open them 5,000 different times in the matter of a second. It doesn't take you any time at all. And so for an example of an HDF5 file, this is a format that's very common for NASA data. This is the basis for netcdf data files. If you're working in the climate or atmospheric space, those are very common there as well. If you're working on a network-based object store, this now costs you a lot more. So just to get to that file takes you now 100 to 200 milliseconds. So that's as much as 1,000 or 2,000 times longer to just get to the file. So that time to first byte is much longer. And so in those situations, you actually have to reorganize the internal structure of your files to make them easier to access into reading these cloud stores. So a good metaphor I like to use when talking about this is if you think about moving, right? If you're moving stuff from like your dorm to the dorm across the hall, you can just like grab stuff. You can just carry a couple of things, you bring them over, you go back to your room, you carry them and bring them over, right? You have to think that hard about like putting everything neatly in the box, packing it up, sealing it, picking up the box, carrying it. You're just going across the hall, going back and forth takes you no time. If you're moving across the country, you better pack everything once because you're going to make that trip only once or at most twice, right? Same exact concept here, right? If you're just grabbing stuff from across the hall, this kind of structure is perfectly fine. If you're grabbing stuff from across the country, you really need to think about how the internal stuff is organized. So what is the performance implication of this? So we've done some benchmarks and you get 10 to 100 times faster read times by using properly organized files for cloud access, for example. And so this is something that we're working a lot on these days, is figuring out how to optimize this for the entire NASA catalog. And finally, just to give you a sense of how this might fit together in the context of like commercial cloud plus also on-prem HPC, this is something I think about a lot with my hat on in our Earth System Modeling office at NASA. You really need all the tools that you have to really combine, to really be able to do the work that we need to get done. And so what I've imagined for our Earth System Modeling office, the Global Modeling and Simulation office where I work, is an architecture that looks something like this, right? So for on-premises HPC, we might have a bunch of process input data. We do our largest scale operational workflows. We might do our largest nature runs or other high resolution experiments, and we might store raw model outputs there. We might connect that to a commercial cloud where we do smaller scale experiments, where we do interactive data analysis on these things, where we might experiment with different hardware options like GPUs or TPUs or whatever PUs are sort of the currently in vogue, right? We might do things like continuous integration or testing, and we might stick our data tools and services there as well. That also has the advantage of connecting to the clouds where the raw data sets are sitting. So commercial data is usually sitting in their own AWS instances, raw NASA data, raw NOAA data, insert whatever. And finally, there's still a place for your computer, right? Like we all have computers that can actually do kind of a lot, right? And so like every time you open a browser, right, a browser actually has a lot of capabilities for visualization, for running code. And so there's a lot of stuff that we can do even on our own machines as well. And so a final sort of strategic version of what a computing environment might look like in a place like NASA might look something like this. Okay, and so last slide is sort of going back a little bit and thinking about history. So show of hands, has anyone seen this photo before? Yeah, so who knows who this is? So this is Margaret Hamilton, 1936, she's still around. She was recently awarded I think a Presidential Medal of Freedom under the Obama administration. She was the lead software engineer for NASA's Apollo project, and one of my personal heroes. She is the one that is credited with coining the term software engineering. So if you look at sort of the origins of that phrase, it originated with her. And it's fascinating reading accounts of software engineers in this era, because a lot of them talk about how, like real engineering was like what the men did, right? And then like all this like other stuff, the software stuff, right? That wasn't real engineering. And so that's what they had the women working on. And so fast forward, like the reason that Apollo was successful, I mean, certainly the hardware engineering, but also in some very, very acute ways, it was the guidance computer during the descent onto the moon that really saved their butts in the end. It was good software design, and it was thanks to sort of a diligence in software engineering. And I say this with some pride because, you know, the software engineering originated with NASA, right? That's where it all began. More obscure is this guy. This is Gordon Moore. You may not have heard his name, but you've probably heard of the company that he founded, co-founder of Intel. And you may not know him, but you may know his law. This is Moore's law. This is the thing that says that every couple of years, the computing capacity will double, right? This is based on the number of transistors that you can squeeze onto a square inch of space. And this is a graphic that's basically proven him right. Notice that there is a log scale on the y-axis here, right? So we are doubling compute capacity pretty much more or less constantly over the course of the last, 50, 60, 70 years. And what's interesting about this is that this is actually also a NASA origin story, right? The original guidance computer for Apollo 11 used integrated circuits, and this is not the standard of practice at the time. They actually used a different circuit model. And so like the reason that they were able to manufacture a lot of these circuits was because NASA and MIT put such a big demand on the manufacture of these chips, that that's what started the growth of this industry. So way back here in the late 60s, early 70s, Gordon Moore was then working at a different company. And so again, it was that government investment in general, and specifically NASA's investment in this technology, that led us eventually to have this revolution in computing that led us to, the phones and the tablets and the laptops and all the other modern computing that we have today. And so all this to say is that at NASA, computing is in our DNA. We think about Earth observations, we think about satellites, we think about rocket launches. But this idea of computing is also something that I think we should take enormous pride in, and I certainly do. Okay, and so I'll stop there, and if you have any questions, let's have them.
Please, maybe we can, I don't know if there's anyone online, but anyone in the room first, have any questions? Just raise your hand.
Yeah.
Thank you for the great talk. It was fantastic. I've been for all of us for this. My question, you mentioned about the web servers that you have contracts with Amazon, and so you go from that channel. It's not possible you develop your own server, because NASA has many facilities. It's not like a small company or.
Sure.
And also another dimension of how you deal with the security of these servers, because they are not within your company or within your corporation.
Yeah, thanks. So for those online, just to restate the question, A, we got a bunch of computers. Why don't we use them to build our websites? And then like B, when we're doing all this cloud stuff, how do we keep it secure? So those two things are actually related. So if you think about like what you need to make a website work, is like you fundamentally need like a bunch of background stuff that's just always on, right? You might need a database. You might need the thing that's like parsing an API request. You might need a bunch of other stuff, right? Like the classic web design is a LAMP stack, right? So that's Linux, Apache, MySQL, and then PHP or something like that, right? And so like, it's not great on the HPC if you've got all this background stuff running, especially if a bunch of people are running it. So that's kind of one of the things where if you actually compartmentalize all this stuff out, it makes more sense. In terms of security, actually, again, what you need for a website is like the outside internet needs to like talk to you. And so like if you are building a website on the same computer that is like doing your mission data processing, that actually exposes it to security risk. And so if you actually separate those two things out, like HPCs are basically driven so fundamentally by security concerns and also by being shared resources that, that it makes it hard to justify doing any of this kind of like web kind of work. Now, what we could do and what we have done historically is just like buy separate dedicated computers and then like run our websites off of those. And that works perfectly fine. And sometimes that's efficient. But again, for some of the reasons that I outlined earlier, like, with the cloud, you can just swap out a new processor when it comes available, but like everything else can keep working. Or you can like swap out a database with a newer database, or you can arbitrarily scale out or down. You can use more or less storage. With a computer, you have to like buy it and then like reconfigure it and do all this kind of stuff and then maintain it. And like buying stuff for you all at universities is relatively easy. Buying stuff in the government is incredibly hard. And so, especially now. Yeah, so that's kind of some of the reasons that it simplifies the procurement, it simplifies the security, by actually isolating all of these things. And like literally, when you access any kind of government thing, like the first thing that pops up is like, warning, you are now in a government system. Yeah, isn't that right? And so like, there's a bunch of security stuff that comes with that banner. And like, when you're on AWS's cluster, you're not on the government computer. And that's kind of the point, is that we can have foreign nationals, we can have people from universities, we can have people from the private sector logging into those resources and using them. And like, that's, that would cause all of our HPC managers' heads to explode if I was doing something like that with our sort of like government funded clusters that we use to also do our mission data processing. Good question. Yeah.
Thanks so much, Alexey, for your presentation. It was such a good overview. My question is something beyond the presentation. I'm more interested to know what you have been working on and what has been the most rewarding aspect of your work.
Yeah, so not about my presentation, what have I been working on, what's been most rewarding? So I wear a couple of different hats at NASA. Maybe I should have started with this. So one thing is I have a small research group, so 2 postdocs and a software engineer, and they're working on vegetation remote sensing. That's where I originally got my start. That's what my PhD research was on. And that's cool. Like the way that NASA typically operates is first we decide what to fly, and that goes through a bunch of complicated sort of decision-making processes. And then like once we fly it, we're just desperately trying to get people to do stuff with what we've flown, right? And so like if you look through the NASA sort of science solicitations, they're often like nominally about science, but like they're really about like, and we really, really, really want you to use this thing that we just spent $600 million on, right? And so the research in my group is all about sort of like opportunistically using some of these measurements, and especially some of the newer ones. So one project that I'm really excited about, led by my postdoc Yoseli Nanhel, is looking at remote sensing of flowers using spectroscopy on the International Space Station. So the International Space Station has this new instrument called EMIT. It was originally designed or sort of intended for mapping the mineralogy of deserts, because that's really important for climate. And if you can precisely characterize like the mineralogy of the deserts, then you can characterize when all that stuff gets blown up into the atmosphere, that's gonna have differential impacts on surface radiation. And like the better you know what the dust is, the better you can know what the impacts are gonna be. So it was originally focused on mineralogy, but spectroscopy is useful for all kinds of stuff. And one of the things it's useful for is studying plants. One of the interesting insights that Yoseli had was that we're already looking at all these deserts, but like one of the things that happens in deserts is like there's not a lot of plants, and then whenever it does actually rain, like all of a sudden there's this massive super bloom of flowers. And so like the fact that this is actually targeting desert areas to begin with is actually kind of like an interesting science opportunity. And it's also one of these things where because these blooms are so transient, this is actually a really good use case for remote sensing, because like we could have a rainstorm in Namibia like in 3 days, and then we'd be like, what am I gonna like grab my bags and fly off to Namibia or like whatever random desert, right? You're not gonna do it. Well, with remote sensing, we actually have the opportunity to see these things everywhere, and so it's a really nice use case for remote sensing. All right, so that's sort of an example of a research project that my team is working on. So the 2 hats where I spend most of my time is, one is I work with the Global Modeling and Assimilation Office at NASA Goddard. So that's the group that does all of those very nice data assimilation schematics that I showed you with the dust and the temperature. So we have like people that are developing the model, and then we've got like scientists trying to make the model better, or like doing interesting stuff with the science. Kelsey and I talked about improving the seasonal forecasting of the model and all the science that goes into that. But then like, we also want to make that model not just be for NASA, but also make it useful for everyone else. And so here, basically, I oversee the group that is trying to get those data into more hands. So like one of the reasons I like to come to places like this and show you really cool graphics from the Global Modeling Simulation Office is to inspire you all to come use our stuff, right? So I'm like selling you sort of the product. So that's part of the job. But the other part of the job is not just selling you on the product, but sort of understanding what is it that you're actually trying to accomplish, right? So Kevin and I had a really nice conversation earlier about irrigation and things like that. And so there's all kinds of hydrology data products that we could provide that could do that. But what, what formats, there's technical stuff like what data formats, what APIs, whatever, do we wanna distribute those in? But also like, which variables do you need? Do you care about root zone soil moisture? Do you care about like total integrated water storage? Do you care about the balance between runoff and evapotranspiration? Do you care about the full 3D profile of the atmosphere, or is all you want like a PM 2.5, nose level thing? And so like going out, asking people that, and then getting their input and then trying to sort of like distribute what people actually need is a big part of my job. And then the last thing is I sort of serve as an advisor to the Earth Science Division on quote unquote data related things. So the really pretentious title that I didn't come up with for that is data strategist for the Goddard Earth Science Division. And so in that context, it's just like we kind of have it down in like how to invest in instruments, missions, airborne field campaigns, things like that. We have like established processes for like funding those kinds of activities. And we don't have good established processes for funding like all this cloud computing stuff that I talked about, or like data science, AI, ML, these sorts of things. And so trying to sort of bring the soft technology to our investment portfolio and figure out how to direct those investments in a way that aligns with our missions that we're trying to do is kind of the other part of my job. So sorry, long-winded answer, but it's a couple of things. Good question, thank you. Yeah.
Can you maybe answer my second question about what's the most rewarding?
Yes, most rewarding. Well, probably like acutely one of my favorite things to do at NASA is actually stuff kind of like this, is to sort of go out and talk to people and understand what it is the science that they're doing, and then try to sort of like align them to specific NASA technologies that can help them. My favorite thing that I did this past AGU was work the NASA booth in the expo hall at the Earth Science Division. And that was really cool because, people come up to me and I'm the like really annoying used car salesman. And I'm like, hey, I bet you're not using enough NASA data. Like, what can we sell you today, right? But actually these conversations end up being a lot of fun. And we can actually talk through like, oh, you're doing coastal bathymetry, like we're not very good at that. That's hard to do. But like some other stuff, you're able to link people to things like the Earth Access Python library, which is a relatively new thing that a lot of people don't know about. And so I think in general, I think in industry, you would call this solutions architecture or sales engineering. But sort of like doing that, but like on behalf of NASA is probably my favorite job. Because I think we have a lot of cool stuff. And I really think it can make a difference to a lot of people's research and also to kinds of applied use cases. So I think when people come use our stuff and then do meaningful stuff with it, that gives me a sense of pride as a NASA employee. Good question.
Is there anyone online that has a question?
Yeah, let's see. Yeah, question online: in this new era of government efficiency, how do you see the balance between on-premises computing and cloud computing going over the next several years, particularly private cloud service providers? Efficiency can be defined in different ways. Boy, can it. Yeah, so I think that it's really hard to do apples to apples comparisons between on-prem computing and cloud computing for a lot of the reasons that I mentioned, right? Because, probably the closest we can do is take the budget of one of our HPCs, which includes not just the facilities, but also the staff and the HVAC and the power and all of that, and then divide it by basically the number of CPU cycles that they run at the data center. And to a first approximation, that's a all-inclusive cost of what that is to run. But where this gets interesting is all of those costs in the bottom half of this slide, right? And it's the labor cost, the collective labor cost of everybody muddling through how to do stuff on the HPC. It is the collective person hours spent waiting around in cluster queues to do things. It is, if you reach hard limits of horizontal scalability in your thing, because your cluster is finite size, right? If you could have done that project 2, 3, 4 times faster, right? That kind of stuff is really hard to capture. And so honestly, one of the things that we're doing right now, and one of the reasons I showed this graphic here is just to give you a sense of this is one version of what this might look like, but I think like one of the really interesting technical parts of my job is like, which of these boxes should go in which dashed line area, right? Is like, should we just abandon all our on-prem HPC altogether and just like eat the cost of doing all this stuff on Azure? Or conversely, like, is it actually more cost efficient to pull some of this stuff out of the cloud and just like buy a bunch of servers like you suggested earlier, and then just like do all this stuff locally? And like, honestly, I have no idea. I do think that it is worth experimenting, and I think that the cloud gives us an opportunity to do those experiments. And that's like actively what we're trying to figure out. But also add that like this is not a NASA specific problem. I mean, I think if you poke around tech blogs, like you see industries going back and forth between like all in on cloud versus then bringing all the stuff back on-prem versus keeping all the storage on-prem but all the compute in the cloud. Like Netflix is actually a good example, I think, where I think they originally went, and somebody correct me if I'm wrong, but my understanding of the history is like they originally went full cloud, everything all the time. And then they're like, whoa, we got too much data. And so then they like built a bunch of data centers specifically for the storage, but then they still do all their like processing and interactive editing and stuff in the cloud. And then like, yeah, you watch Netflix tech blogs from 10 years ago, and they're very different from Netflix tech blogs from 7 years ago, and they're very different from Netflix tech blogs from 4 years ago, and they're very different from Netflix tech blogs from a year ago. And so like this space is constantly evolving, the cost efficiency trade-offs are constantly changing. Here's some spin. That's, I think, one of the advantages of having an environmental data analytics program like you guys have here, right? Is I think that like it is really, really important to be a successful scientist. I think to like learn from what industry is doing, to have at least some sense of what's going on in sort of like the software engineering space, because there's all kinds of problems that they've solved that we don't even know they've solved for us. And then, it's also useful to know like what problems aren't actually solved and where there's room for sort of interesting computer science research that could have, both industry benefit and also, public sector research benefit as well. So, yeah, let's see.
Maybe one more there than one in the room if anyone has it.
Yeah, that's true. Yeah, I mean, there's a comment here about if only budgets scale the way cloud compute resources scale. I think your general idea of doing the pricey stuff on-prem while automating more in cloud is a good affordable model. Yeah, thanks. I mean, I think again, like it's also, if you haven't worked in the government, it's hard to overstate just how awful the bureaucracy can be around things like procurement. And that like that adds a whole other layer to the bottom of this chart. Is like, should it, in theory, like if I have a credit card, it should be about the same for me to like walk into Radio Shack and buy some parts versus like renting them from the cloud. Like in practice, for very weird, strange reasons, those two things are very different. And so like, because NASA has big institutional agreements with AWS, yada, yada, this and that. Yeah, there's things that we are subject to when we buy physical hardware that we are not subject to when we rent it from the cloud. So there's all kinds of just silly government stuff that sort of gets in the way here as well. And that constrains our decision space in interesting ways.
Any last question? All right, well, thank you very much.
Thanks for having me. Thank you.
Good overview. We can sit here. Meeting and stuff.